How are you today? Today we are going to start discussing on a totally new topic on reactions of alkyl halides, which entails substitution and elimination reactions. Alkyl halides can easily be converted to many other functional groups, and the halogen atom can live with its bonding pair of electrons to form a stable halide ion, as we've seen in most of the cases when we're discussing on the synthesis of alkyl halides. We say that a halide is a good living group. When another atom replaces the halide ion, the reaction is substitution. And when the halide ion leaves with another atom or ion, often a proton, the reaction is elimination. You will see later. And in many eliminations, a molecule HX is lost from the alkyl halide to give an alkene. So that's how alkenes are synthesized. Such eliminations are usually called dehydrohalogenations to indicate that the hydrogen halide has been removed from the alkyl halide to form alkenes. Substitution and elimination reactions often occur in competition with each other. You will see that later also. So we'll start with discussing substitution reactions of alkyl halides. So in a nucleophilic substitution, a nucleophile, so an electron-rich species, replaces a halide from a carbon atom using its lone pair of electrons or negative charge to form a new bond to the carbon atom. So this is general reaction without necessarily showing the mechanism, whether it's through SN1 or SN2. So you have the carbon, which is bearing the halogen. Again, we said this is the reactive center because this bond is polarized, then can easily break and another one formed. And then this carbon also is electrophilic. Then the adjacent carbon, if it's bearing hydrogen, you'll see later that it can also be lost along with the halogen to form alkenes. But in nucleophilic substitution reaction, what happens is another nucleophile, electron-rich species. You can see this is an electron-rich species. We don't know which particular one it is, but it has addition. It has two electrons which can easily be used to form a new covalent bond. And of course, when you see it like this, then it means it has 8 electrons. There's a negative charge, so it has or available to each 2 electrons or a covalent bond that it can easily form with electron lacking species, like in this case, this carbon, which is bonded to the halogen, which is electrophilic because of electronegativity of the 2 atoms is not similar, with halogens being more electronegative, and therefore the electron density will always be pulled towards the halogen. Therefore, the halogens will have some partial negative charge and the carbon will have some partial positive charge. That's why any nucleophile is going to donate electrons to form a new bond with the electrophilic carbon, which is bonded to the halogen, and the halogen leaves, and it's a good living group because it's relatively stable once it leaves. So here you can see the halogen. This is an alkyl halide. This is another nucleophile, and there are a variety of them which can react with this electrophilic carbon to form different variety of products. So there is now a bond to the nucleophile, and the halide is a living group. So alkyl halides are very good substrates for synthesis of a variety of products or reagents. For elimination reactions of alkyl halides, in elimination, both the halide ion and also another substituent are lost and a new pi bond is formed. So, but to facilitate that, you always need a base for that reaction to take place so that you have a double bond which is formed in the long run with a halide, and also you can see a base which is bonded to the hydrogen or this acidic proton on adjacent carbon. So what will happen is this base will abstract this hydrogen. So one of the requirements is that on the adjacent carbon, there should at least be a carbon-hydrogen bond. So that hydrogen is the one which will be abstracted. So the base is just like a nucleophile rich in electrons, but it will only form a bond to hydrogen or a proton. So it donates electrons to this hydrogen and this proton, because it will leave when it is positively charged, and the two electrons will be left behind, will form a new bond and then expel the halide. So you can see, so this is the abstracted, then this is going to form a bond, then the halide is the leaving group. In both cases, in elimination and in nucleophilic substitution reaction, the halide is always a good leaving group. So it's the one which leaves during these two processes. So this is generally an elimination reaction. So one of the most important reagent that is required is the base to abstract the hydrogen or the proton on adjacent carbon, adjacent to the carbon which is bearing the halogen. In elimination, a dehydrohalogenation, the reagent B, the negative, reacts as a base, abstracting a proton from an alkyl halide. So these processes, we are going to discuss them later. Most nucleophiles are also basic and can engage in either substitution or elimination, depending on the alkyl halide and the reaction conditions. So depending on the reaction conditions, you can either get an alkene or you can get a substituted alkyl halide. In addition to alkyl halides, many other compounds undergo substitution and elimination reactions like alcohols. The only difference, as I've said, is that for alcohols, the first step is to convert the hydroxyl group into a beta leaving group, and also to make the carbon which is bearing the hydroxyl group more electrophilic so that it can react with different nucleophiles or bases to form double bonds or alkenes, or so that it can react with other nucleophiles to form, so that the hydroxyl group can be substituted for by other groups. So we'll start discussing the second order nucleophilic substitution reactions, which you've heard me talking about, that is the SN2 reaction. So again, a nucleophilic reaction has a general formula. So you have the nucleophile, which is rich in electrons. And we have different nucleophiles. You have the strong nucleophiles and the weak nucleophiles. The strong nucleophiles are the ones which are negatively charged, like the one which is presented here is because it has a negative charge. These are the strong nucleophiles, which are rich in electrons, which are ready to use to form a new bond with electrophilic or electron lacking species. Then we have neutral molecules, so long as in that molecule you have an atom with a lone pair of electrons, like water, for example. Alcohols, for example, oxygen has a lone pair of electrons in alcohols. You have also ammonia, for example. The nitrogen in ammonia has one lone pair of electrons. So those are all nucleophiles, but they are weaker nucleophiles than the negatively charged nucleophiles. And I said another class of nucleophiles is double bonds and triple bonds, and it's because of the accessibility of the pi bond, one in the alkenes and two in the in two in the alkynes. We also have the benzene ring or aromatic compounds also being rich in electrons. So the most important thing to note for alkyl halides are good substrates for these nucleophilic substitution reactions, because these halides are very good leaving groups. So they can easily be substituted for by different nucleophiles. So here we are showing a strong nucleophile. So this can come, form a new bond. So use the electrons that it has, form a new bond with this electrophilic carbon, the carbon which is bonded to the halogen. And this halogen atom leaves with the two electrons of this covalent bond, forming the halide ion. So it's usually a good leaving. It's known as a good leaving group. So there'll be a new bond to this nucleophile. So we don't know which nucleophile it is. And nuc is just general for different nucleophiles. So there'll be a new bond to the nucleophile, the new nucleophile, and there will be a halide ion which will be eliminated from the reaction. So finally, so this is a normal general form of nucleophilic substitution reaction, without necessarily saying that they are undergoing or proceeding through SN1 or SN2. All the nucleophilic substitution reactions, with the alkyl halide as a substrate, always have the halide as the leaving group, and then the nucleophile donating electrons to the electrophilic carbon, forming new bonds. How they form the new bonds, and how the halide leaves, that's another step. That is what now defines the SN1 or SN2 reactions. An example is the reaction of iodomethane with potassium iodide, where the product is methanol. So this is one way in which this is how methanol can be synthesized, by reacting iodomethane and hydroxide ion, which is a nucleophile. In this case, we have now this specific nucleophile and this specific alkyl halide reacting to form these products. For example, if you wanted to synthesize methanol, and also the iodide ion is a leaving group. So you will note that here, okay, this is supposed to be HHH. Okay, the way it's presented is wrong. It's supposed to be HHH so that it's a methyl group. So this is a specific alkyl halide, and the nature of this alkyl halide is a methyl alkyl halide, or a methyl halide. So you have carbon, hydrogen, hydrogen, and hydrogen. I'm going to insert those hydrogen atoms so that you don't get confused. Then the hydroxide, this is the nucleophile, and this is a strong nucleophile. So you have a strong nucleophile, you have a methyl halide forming methanol and iodide ion. So this is said to be undergoing SN2. So let's just go down. So the hydroxide ion is a good nucleophile. So you can see in this particular reaction, which we will call SN2 later, is that the nucleophile which is reacting is a strong nucleophile. So the donor of electrons should be a strong nucleophile. So the nucleophile is a strong nucleophile in this case, and it's because the oxygen atom has a shared pair of electrons and a negative charge. So the ones which are negatively charged, as I've said, are strong nucleophiles. Iodomethane is called the substrate. So the alkyl halide is usually the substrate, and it means a compound where that is attached by, or is attacked, not attached, attacked by the reagent. The reagent in this case is a nucleophile, or it is a compound where the reaction takes place. So that is usually known as a substrate. So in this case, it's an alkyl halide, and sometimes you can also have alcohols as substrates, as you saw in the synthesis of alkyl halides. In that case, the substrate was the alcohol where the reaction is taking place. So the carbon atom of iodomethane is electrophilic because it's bonded to an electronegative iodine atom. That one we already know. So here it's showing. So the carbon is attached to electronegative atom, which is the halogen. Here in this case, this halogen is iodine. So when you have these, the two atoms forming a covalent bond, because iodine is more electronegative, the electrons tend to move towards, the electron density tends to move towards iodine, the more electronegative atom, causing the carbon to have a partial positive charge. So it's the one which is going to attract the electrons which are negatively charged. So the next step, again, you can see here, the electrons are donated to this carbon. And then finally, you have the leaving group, which is the halogen or the iodide. But we have not shown the mechanism, how it's going to take place. So we are assuming this is just general representation of what the reaction, how the reaction generally takes place. You have the nucleophile donating electrons to the electrophilic carbon, then the leaving group leaving, and finally you get the product. So hydroxide ion attacks from the backside of the electrophilic carbon atom, donating a pair of electrons to form a new bond. So this one is already defining the mechanism in which this particular reaction is taking place when you have a strong nucleophile and you have also a methyl halide. So this is now showing the real structure. This is a methyl halide. So you have carbon here, which is bearing the halogen is attached only to hydrogens. So this type of substrate in this case, and also primary alkyl halides, they always undergo SN2 or mechanism, and you always have to have a strong nucleophile. And in that, when it is SN2, the nucleophile always attacks from the backside of the electrophilic carbon atom, donating a pair of electrons to form a new bond. In general, nucleophiles are said to attack electrophiles, not the other way. So you have nucleophiles attacking electrophiles. In this case, electrophile, in this case, is the carbon, which is bearing partial positive charge. Nucleophile is the hydroxide ion. Also notice that arrows are used to show movement of electrons from the electron-rich nucleophile to the electron-poor carbon atom of the electrophile. So you have to always show the arrows correctly because you are moving from electron-rich, because it has electrons to donate, to electron-lacking. It has to donate to that particular species which is lacking in electron. So the arrows always shows from electron rich to electron poor. So from nucleophile to electrophile. Don't draw the arrows opposite, but students always do that. So ensure that you are drawing the arrows correctly from electron rich to electron poor. Then carbon can accommodate only 8 electrons in its valence shells. So the carbon iodine bond must begin to break as the carbon oxygen bond begins to form. So immediately, let's go to the next. Okay, I can't see it. Okay, it is down there, the mechanism. So iodine ion is a living group. It lives with a pair of electrons that once bonded it to the carbon atom. So that is also another thing you need to note for SN2 reactions. So this is the general mechanism. So the first thing is for you to have SN2 reaction, you need a strong nucleophile. We've talked about that. So this is a nucleophile, the hydroxide ion. You need an unhindered substrate, like in that case, alkyl halide. So this is an unhindered substrate or alkyl halide, where you have carbon which is bonded to hydrogens. Hydrogens do not hinder this carbon which is a reactive center, or which is bearing the partial positive charge. That is where the reaction is taking place, and by electrons being donated to it to form a new bond. So since it has only hydrogens, and it's not hindered. But if it has alkyl groups around this carbon, which is bearing the halogen, which is electrophilic, then it starts becoming hindered. So for primary alkyl halides, they are not very hindered, but secondary is more hindered than primary, and tertiary is completely hindered, because remember, each of the alkyl groups, always the carbon is sp3 hybridized, and it is directed to the corners of a tetrahedral. So it occupies a lot of space. Hydrogen doesn't. So in that case, when it is unhindered, so for SN2 reaction to take place, it requires a strong nucleophile. The substrate or the alkyl halide should be unhindered. Even alcohols undergo SN2 reactions, and the properties are the same. They need a strong nucleophile, and they also need unhindered substrate. So the first step is where the nucleophile will donate its electrons to form a new bond with this carbon, which is electrophilic. And then, so another thing is you have to note is that as this bond is trying to form, this bond will also be trying to break, and therefore there will be a transition state which is pentavalent. So 1, 2, 3, 4, 5. So this is very unstable, and it's a high energy state. And because of it has 5 covalent bonds, while carbon should always have 4 covalent bonds. So immediately that happens, this bond now will break completely, and the 2 electrons will leave with the iodine as iodide leaving group. And then this bond to the hydroxyl group will also form completely. So you can see here it is blue. It's highlighted in blue, meaning it's the one which is donating the covalent bond. The hydroxyl group is the one donating the 2 electrons to form this covalent bond. Then this green part is just showing that these 2 two electrons of this covalent bond are leaving with iodine to form the iodide leaving group. So those are the things you need to know about SN2 reactions. So that's how the mechanism of SN2 reaction. You need a strong nucleophile, unhindered alkyl halide. The reaction the reaction proceeds through formation of a transition state, which is pentavalent. Then finally you get the product and also the leaving group. And we said iodine or any alkyl halide halogens are very good leaving groups, and they leave as halides. So it's important to note that the reaction of methyl iodide, that's iodomethane, with hydroxide ion is a concerted reaction taking place in a single step with bonds breaking and forming at the same time. So it's not a many steps reaction, it's a concerted reaction, which is a one-step reaction with bonds breaking and forming at the same time. So that's very important to note. The middle structure is a transition state, a point of maximum energy rather than an intermediate which can be isolated. So this is just a transition state and not an intermediate that can be isolated, and it's a point of maximum energy because again we said it's very unstable, so that is why it is a point of maximum energy. In the transition state, the bond to the nucleophile, that is hydroxide, is partially formed, and the bond to the leaving group, that's iodide, is partially broken. That we've already indicated. Then remember that a transition state is not a discrete molecule that can be isolated. It exists for only an instant. From reaction energy diagram for this substitution, there is only one transition state and no intermediates between reactants and products. You will see that later. The reactants are shown slightly higher in energy than the products because this reaction is known to be exothermic. Sorry. So the transition state is much higher in energy because it involves a 5-coordinate carbon atom with 2 partial bonds. You've seen how that's what I mean, or it's even here, the energy diagrams. So this is trying to form, this is also trying to break. So this is a 5, it's like 5 covalent bonds almost, though these ones are not complete, it is very unstable. So these are the reactants. This is alkyl halide, for example, iodomethane. Then this is a nucleophile, hydroxide. This is the energy level. They are at a lower energy level, of course, more than the transition state, which is the highest energy level state and very unstable. Then after that, once this bond breaks and this bond to the new nucleophile forms completely, then the energy drops down to even a lower energy level that's compared to even the reactants because this is an exothermic reaction. So the products are at a lower energy level as compared to the reactants. So the one-step mechanism is supported by kinetics information, and one can vary the concentrations of the reactants and observe the effects on the reaction rates, how much methanol is formed per second. The rate is found to double when the concentration of either reactants is doubled. So if you double the concentration of the hydroxide ions, then the rate of reaction is doubled. And if you also double the rate of the concentration of the alkyl halide, that's iodomethane, also the rate is known to double. So the reaction is therefore first order in each of the reactants and second order overall. So this is the rate of reaction, which is dependent on the concentration of the substrate. Okay, this is the specific substrate in this specific reaction, iodomethane and the hydroxy and the concentration of the hydroxyl group. This mechanism requires a collision between molecules of methyl iodide and hydroxide ion. So both of these species are present in the transition state, and the collision frequency is proportional to both concentrations. Therefore, the rate constant depends on several factors, including the energy of the transition state and temperature. And this one-step nucleophilic substitution is an example of the SN2 mechanism. Why SN2? Because it's a substitution. So S is for substitution, N is for nucleophilic, and 2 is for biomolecular, because the rate of reaction is dependent on the concentration of the two reactants. That's the hydroxide in that case, or the nucleophile if it's general, and also the substrate, which is in this case the iodomethane. So the rate of reaction is dependent on the substrate and also the nucleophile, the concentration. So that's why it's biomolecular, or 2. The 2 is for that. The term biomolecular means that the transition state of the rate determining step, only one step in this reaction. Remember this particular reaction or mechanism is a one-step reaction. It doesn't have two steps. It's a one-step reaction. And the rate of the reaction is determined by the concentration or the collision of the two molecules. Bimolecular reactions usually have rate equations that are second order. So this is for you to do. So under certain conditions, the reaction of 0.5 molar methyl iodide with 0.5 molar sodium hydroxide forms methanol at a rate of 0.05 moles per liter. What could be the rate of if 0.1 molar methyl iodide and 2 molar sodium hydroxide were used? Of course, when you see this, you might start asking, hey, where is the hydroxide? Where is what? Of course, when you see sodium hydroxide, that is the source of the hydroxide ions. So the hydroxide ions cannot exist on their own. They are stabilized by the sodium ions. So when you see hydroxide ions, then you know that is the source of the nucleophile or the hydroxide ions. Many useful reactions take place by SN2 mechanism. The reaction of an alkyl halide such as methyl iodide with hydroxide ion gives an alcohol, but you can have others also, primary and also methyl halides with other nucleophiles forming other products. So other nucleophiles convert alkyl halides to a wide variety of functional groups. So next time we will discuss about the halogen exchange reactions. Thank you.